Hello everyone, Jan here. Take a look at our home, our pale blue dot. Ever wonder how people figured out how to navigate across the world? How was our round Earth put on a flat map? It's definitely not because our Earth is flat. Here is an example of a stereographic projection map of the northern hemisphere. Stereographic projection is a way for every point in Earth to be mapped. Usually this only maps one hemisphere, since the continents and the outer edges become too distorted and inaccurate. Let's talk about how stereographic projection works. The sphere, or in this case Earth, is placed on a plane, intersecting at one point, which is usually a pole. A projection point is placed on the opposite polar point of the sphere. You can think of the projection point as a light source, casting shadows within the sphere. Each landmass can be seen as an opaque object, blocking light. This occurs for all points in the sphere, minus the projection point. This produces the resulting round map for stereographic projection. Just based off this construction alone, you can notice a few things. One big advantage of stereographic projection is that angles are preserved, otherwise known as conformal. We will see an outline of the proof of this later, but just by visuals alone, you can see that it is conformal with the angles produced by latitudinal and longitudinal lines. Notice that the right angles created by these lines are also preserved on the plane, as right angles as well. Another thing we notice is landmass shapes are preserved, however their size isn't accurate. The further the landmass is from the intersection point, the more distorted the size of the landmass is. This also means that mapping distances closer to the projection point are more accurate, hence why stereographic projection maps are used more for polar region navigation and topography. Now let's define stereographic projection with math. Point P in the sphere would have an equivalent point P' on the plane. P' would be found from P by tracing a ray from the projection point to the plane. Since each point in the sphere can be mapped, the resulting rays produce a cone shape. Note that there are other constructions of stereographic projection. The radius of the cone can change by increasing or decreasing its radius, or the projection points can be defined differently. For example, we can use the North Pole as our projection point, and the South Pole as our intersection point. Even the plane itself can be placed differently. For example, the plane z equals 0, where the plane is in the equator of the sphere. But for the following section of the video, we'll focus on using the tangent point on the North Pole. The projection point will be on the South Pole. The projection point, with a cone inside the sphere, points in the plane can be expressed with the following formula. The inputs will be points in the sphere with coordinates x, y, and z. The inverse mapping is the following. This gets the point on the sphere given a point on the plane, x and y. Now let's explore two properties of stereographic projection. First, any circle on the sphere is mapped as a circle on the plane, as long as that circle does not pass through the intersection point. Let's construct a triangle A, B, and C inside the cone, along the axis of the cone. Let's call this the axial plane. Inside triangle A, B, and C, let's make triangle A', B', C, constructed with opposite angles of A, B, and C. Intersecting line segment A', B', let's create a plane perpendicular to the axial plane. Now that we have the section of this cone, we want to prove that it's indeed a circle. In typical math fashion, we leave that to the viewer, but the proof is listed in the description below. Now back to stereographic projection. Why does this proof about cones prove that circles on a sphere also map as circles on the plane? The circular base of the cone can be seen as the projected circle on the plane, and the circle at the base of triangle A', B', C can be seen as a circle on the sphere. This showcases the first property of stereographic projection. Our second property is that stereographic projection is conformal. This means that angles created by the intersection of two curves on the sphere are also preserved on the plane under stereographic projection. We already know that the curve created by latitudinal and longitudinal lines preserve right angles based on observation. Now, let's do the fun work and explore what it means within math. Okay, let's start. First, let's define the longitudinal line we'll use. It will be created with the North Pole and the South Pole. Next, let's create a triangle along the longitudinal line, with point P tangent to the unit sphere. It will also have a right angle perpendicular to the line created with the North and the South Pole. Angle alpha is created by two great circles with P as the intersection. A great circle is a curve that has the same circumference as its sphere. This longitudinal line is one such great circle. A possible great circle helping produce angle alpha could be parallel to the hypotenuse. Now let's imagine stereographically projecting triangle PQR to a plane on the South Pole. Let's call this triangle P'Qr. Angle alpha would be projected as angle beta. With these triangles, we want to prove that angle alpha is equal to angle beta. If we prove that, then we can prove that angles are preserved between the sphere and the projection. Quick disclaimer, this proof is a little tricky, so feel free to check out the source below. I'll only cover the outline of the proof in the video. To start, notice that triangles PQR and P'Qr share the same common side QR. So if you can prove that PR and P'R are equal in length, then you can use tan to prove that angle alpha is equal to angle beta. If you want line segment PR and P'R to be equal in length, then that would mean triangle RPP' would be isosceles. Using the triangles laid out in the longitudinal lines plane, we can prove that triangle RPP' is isosceles, which in turn proves that angle alpha is equal to angle beta, which also in turn proves conformality for stereographic projection. Given these properties, one can see the use of rigorous math within grand real-world applications, as well as aid us in our adventures. I hope this video gave you a deeper insight into stereographic projection and the math behind it. This wraps my quick animation on stereographic projection. I listed my sources for research and the proofs in the description below. Thank you for watching and see you next time.